So we are working on Electrician Theory Exam ET37, 20th November 2010. And we're going to start doing a mathematical question. So it's not that one. Question 1H. Calculate the power factor of a small three-phase printing factory with mainly motor loading. Meter instruments have recorded the following information. Power, 30,000 watts or 30 kilowatts. Volts, 406 volts. Amps, 57 amps per phase. Okay, so with our power factor, we are working on a power factor triangle. So we know this is our VA, this is our VAR, and this is our watts. So we have 30,000 watts. This one here is our VA, so it's 57 amps times our 406 volts. And now we get our calculator and just 57 times 406, and we get 231,231.42. My mistake there is this is three-phase VA, so not that one. It's so instead of VA equals root 3 times VA equals V times A, our power factor formula is actually VA equals root 3 times V line times I line, which in this case is root 3 times V line, which is our 406 volts, times by our 57 amps, and equals, so times by root 3, and we get 40083.119, so 12 VA. The reason I knew I'd made a mistake immediately is on this triangle, if I do it by square root of 3, if I did my original calculation, this line here will always be shorter than this line on a right angled triangle, right? And I got a value when I first worked out of 23,142, which gave me an automatic reminder that I'd used the wrong formula. I should use the three-phase one, not the single-phase one, as per the question. Makes sense with 406 volts as well. So now our power factor is this. That is our power factor in degrees or in a value. The value is simply, and because it's always going to be less than 1, going to be W divided by VA. If it was VA divided by W, we would end up with a value bigger than 1. So that's how I know the formula each time I do it. So my P dot F equals W over VA. So equals our watts is 30,000 over our 40,083.12. And putting that in our calculator, we get 0.748, so 75. Rounded to 2 decimal points. And if we go to our answer sheet, sure, this was the answer sheet for this one. Maybe it's not. Yeah, that's correct. So it's 8. Yeah. Right. They went to 3 decimal places in this one, so 0.7484, so 0.748 is what they used. Nowadays, in the modern exams, it asks you to go to 2 decimal places, not 3, but as you can see, that matches. So we are looking at question 2 now, part B, and this is of 20th November 2010, ET37. So, an earth loop impedance test result of 0.32 ohms has been recorded on 230 volt final subcircuit, supplying socket outlets and a low voltage outlet electrical installation. Calculate the fault current that will flow if a short circuit occurs on the final subcircuit. So what they're asking here is we've got transformer and then we've got our socket. And we've got a short circuit, which will be between our earth and our L1. So we have a short circuit here between those 2 points. They've calculated our impedance of 0.32 ohms, and our voltage between here and here is 230 volts. So it's a simple single phase question here. The difference is we're using impedance instead of resistance. That is just because we're dealing with coils of wire as part of the transformer, ultimately for our calculation. Impedance is a calculation of the total resistance in both XL or XC as well. So our formula in this case is A equals V over Z. So equals 230 divided by 0.32 equals 230 divided by 0.32, and we get 718.75 amps. Okay, so we are working on question 3. This is of 20th of November 2010, ET37. So our question is, primary of a three-phase delta star transformer is connected to a three-phase supply, secondary line voltage 400, turns ratio is 2,859 to 20. When the transformer is fully loaded, the full load primary line current is 4.37 amps. Assume there are no losses in the transformer. They want us to first calculate the primary voltage. The first thing I'm going to do is actually draw this. So this is delta star. So I've got our delta, our star. We know that our secondary line voltage is 400 volts. And we know that our amp here is 4.37. Our turns ratio is 2,859 to 20. So first we need to work out our voltage of primary to primary. So we divide our 400 by the square root of 3, which you'll probably know is going to be close to 230 volts. And we're getting 230.94. 94. Sorry, bad handwriting. So 230.94 volts. So that's our prime, our phase voltage. So that'll be between there and there, which will match up with here. Now what we do is with our ratios, we can just divide by that to get our volts per turn, then multiply by that to get our volts on that phase. So divide by 20 times by 2,859, and we get our 33,012 volts, 0.888, so 89 volts. Now, they wanted our primary voltage. That is our primary voltage. So, if we check our answer sheet, they've got, because they've rounded, they actually end up with 3307 volts. They're slightly out from rounding, as they've done in the question, but because we use 9.4, well, the whole thing, and they rounded it down to the 0.9. You do you, both will be marked correct in an exam because there's a certain amount of rounding error. The next question they're asking us, and we're going to leave our drawing out because it makes our life easier, calculate the full load kVA rating transform. Full load kVA rating transform. Now, the easiest one to do is this side is we're working with three-phase and we need volts and amps. So working it out on that side, our three-phase kVA, or let's just do VA to start with, equals root 3 times I line times V line. In this case, we've got root 3, easy, that's constant, times our I line, 4.37 times by our V line, which is 33012.89. That's still in the calculator, so I can just multiply that by root 3 to get out of the square root, so I don't screw that up, and then times by our 4.37, and we get VA equals 249,876.6 VA. We need to work out our KVA. So we just move our decimal place 3 to the left, which gives us 249.87. So 876, so we round up 88 kVA. And if we look at our answer schedule, because they've used the rounded value, they ended up being slightly off, but it's basically the same formula, 249.92, where we've got 88. So it's not very clear. Next, we are working on the secondary line current. Now, easiest way is actually using this formula again and working our way backwards, since we've already got the kVA and we've got the line voltage to start with, which is 400. So our formula in this case is VA equals root 3 times I line times V line, just like before. But now, because we're calculating I line, we want to rearrange it. So we divide by root 3 times V line, and on this side we have to do the same, root 3 times V line, and then the root 3's cancel and the V lines cancel. So we end up with VA over root 3 times V line equals I line. We substitute in our values, so our VA was 249.87, 6.6 over our root 3 times 400. Carrying that over, so that's substituting our values there. And so we get, if I divide by root 3 times 400, and you'll notice I had to put that in brackets because they're implied when you do a line like that, and we get 360.665, so 67 amps. Grab the answer sheet. They rounded up a little bit more, so 360.7 amps, both correct within margin of error. The next one they want is the regulation of the transformer. Now, on your formula sheet, this is the regulation of a transformer one here. There is some debate about this. This is no load, full load, not full voltage and reduced voltage. So full voltage is actually the no load, full load is the reduced voltage. And this value on the bottom, actually, there's some debate on which is the right way this formula goes, which this said that this formula sheet is wrong. You'll see that in the exam that they accept both values. So we have our question. Question. So got that, calculate the secondary line current, which was our 360.67 amps. And now we're doing at full load, the voltage dropped to 222 volts. Calculate the percentage regulation of the transformer. So to our original page, we can see our starting voltage is 230.94 minus our 222 over 222, filling in our values, and that then all gets multiplied by 100 to get our percentage. So V reg equals, from our formula sheet, so 230.94 minus 222 equals, and divided by 222, and we will get 0.04. I forgot to times by 100. So 4.037, so 0.03%. However, if you also do it 230.94 minus 222, and then divide that by 230.94 times by 100, you would get equals 3.871, so 87%. If you look at the answer sheets again, so in the answer sheet, you can see they were letting you do 3.85 or 4% because there's regulation and alternative regulation, whichever formula you're actually after in this particular situation.
Okay, so we're doing Electrician's Theory Exam, 20th of November 2010, ET37, question 7. So, metering in a small 400 volt 3-phase 4-wire commercial installation has produced the following results. Red 60 kilowatts, white 173.91 amps, blue 82 kilowatts. Assume unity power factor. So that means assuming a power factor of 1. Calculate the total power of the installation. So first one, total power, we already know we've got 60 kilowatts and we know we've got 82 kilowatts. And our last one, we're just calculating a white phase where we've got 173.91 amps and 400 volt 3-phase. We need to work out our single phase. So our single phase is 400 divided by square root of 3 to give us our individual voltages. So 230.94 volts to our neutral, and then power equals volts times amps. Power equals 230.94 times our 173.91, and times our 173.91, and we get 40162.79. We're going to round this into kilowatts just like the others, so that would be 40 kilowatts, giving us 40 for that one. So 40 plus 60 gives us 100, 182, so 182 kilowatts total. If we look at our answer sheet for this one, they have 60 plus 39.99 plus 82, so they must have used 230 instead of 230.94, and 181.99 kilowatts. We're actually, once again, more accurate than the answer sheet. And they were actually rounding down instead of up. Small differences matter. But at the same time, for these exams, there will be a fudge factor when you're doing it, where they expect you to be out by rounding errors, because clearly they are. Next, we go on to part B. Determine the neutral current. So, there's a few ways to do this one. My preferred method is not a way that you're going to see anywhere else. But we have our 3 slots. We've got our 40, our 62, and our 82. So those are our kilowatt values. We then essentially draw a circle around, and we know that we're clipping off 40 of each. So 62 minus 40 leaves us with 22, 82 minus 40 leaves us with 40. So that's our kilowatt values, 22 and 40. Next we go long side, 40 kilowatts. That angle there we're going to do at 22 kilowatts, and then we're drawing a rhombus. So it's essentially 90 degree there, 90 degree there, that's 60, that's 60, right? And that one there will be our 120. The neat thing about this picture, and you can draw this with a protractor or a ruler and measure it off, and that will generally be accurate enough for the exam. that is our neutral kilowatt value. All right. Now, this will always be half of that, so that'll be 11 kilowatts. And this one, here, this length here will be the same as that one. So 40 minus 11, that gives us 29 kilowatts. And then, because this is a right angle triangle, we could use Pythagoras to get that one. So that will be 22 sine 60 kilowatts for the vertical. And we can just use Pythagoras. So squared plus our 29 kilowatts squared, and then we can get the square root of that, and that equals our neutral kilowatts at 230.94 volts. So if we pull out our calculator, 22 sine 60 equals square that plus 29 squared, and then we get the square root of answer, and we will get 34.698, so 70 kilowatts. And now we divide that by our voltage, which is 230.94. So divide by 2, multiply it by 1,000 first, so that we're getting watts, and then divide by 230.94, and we end up with 150.249, so 25 amps. And if we look at the answer sheet, it says I equals 150 amps, except any answer between 145 and 160. So we got 150.25. So that's the most accurate answer. Basically, we did round slightly for the 40 kilowatts, but as you can see, we're well within their fudge factor. The alternative method to do this, which I'm not a fan of, is using the formula in the bottom of our aspect sheet. So if we pull out our aspect formula sheet, where did I put that? So if we pull out the aspect formula sheet, we have this neutral current calculation here. Now you're always allowed to use this, it's just going to be less friendly to use and a lot more typing in the calculator. And the way this works is we're using our triangle where we've got our three phases now going internally, and the neutral current is that one. So we've got red, white, blue, doesn't really matter on the three, it's just longest, second longest, third longest type of thing. And then our point from there to there is our neutral current. This is 60 degrees, this is 60 degrees. It's a right angle it's an equilateral triangle, so if all three matched, you would have zero neutral current, and that's our balanced load explanation. But to use this one, we actually have to calculate our individual values. So the formula says A, B, and C. You can also use red, white, and blue as an alternative letters, RWB, and it would be the same formula. So R equals A, W equals B, B equals C type thing, just to be weird. Could have B equal B. But you could use either red, white, blue, or ABC for our letters, and then N equals N for our neutral. So when we go back to our previous values, that makes it easier. So we have red 60 kilowatts, white 173.91 amps, and blue 82 kilowatts. To use this formula, we have to actually first convert the kilowatts into amps. So 60 kilowatts, so 60,000 divided by 230 point, sorry, what was my number again? Just 94. Just placed page. Let's just reconfirm. So it was 400. 400. And we get 259.80 amps. And for our other one, we have 82,000 divided by. And we have 355.07 amps. So for our three sides, we're going to have 355.07, 259.80, and 173.91. And we are trying to work out our N. So for our formula, what we have to write down is N equals square root of, and then we've got bracket 355.07 squared plus 259.8 squared plus 173.91 squared minus, and then we've got 355.07 times 259.8 brackets, and then this is just carrying on from there. So that's that times that, and then we do that times that. So 355.07 times 173.91, and then we do that times that, or minus that times that. So 259.80 times 173.91 in brackets. I hate typing this one in. You'll see why I like the other version as I go through this. So first, put in that bracket is the easiest way to put it in the calculator. So 355.07 squared plus 259.8 squared plus 173.91 squared equals. So that gives me the total of that bracket. Now I minus off my next value. So minus, in brackets, 355.07 times 259.8. And I can press equals, and then I can minus the next one. So minus bracket 355.07 times 173.91, this bracket equals, and then minus that times that. So 259.8 times 173.91 equals, so I've minused off those three values. I now have the total result of that. I get the square root of answer, and we get 156.96. So our numbers are very close, and that will still fit inside our calculation. So one answer sheet. Here. There we go. So before we got closer to the 150 amps, because we didn't have rounding issues from writing in the values without any of the end, and when you're squaring. So that's one of the reasons why they have our I equals 150, and when we calculate it this way, we got 156.96, even though that's actually less accurate than our previous calculation, because we had to round in the middle. The last option, of course, and I don't have the tool set up here, is you can draw this triangle here. And if you actually draw it to scale, with that is 60 degrees, that is 60 degrees, and you use the amps as the length, you will get the same value once again. and you can see their parts as you go through. Okay, so now we are looking at 20th of November 2010 ET37, and we're looking at question 8. So, from the information on the nameplate, state the power factor of the motor. So we're looking at a motor nameplate in this one. So the power factor is pretty easy. We're looking for cos theta, typically for power factor, or a P dot F. So in this case, it's using cos theta. We've got 0.82. That is our power factor, so 0.82. Easy question for A, we just read it off the nameplate. So P dot F equals. Next one, using the information on the nameplate, calculate the output kilowatt rating of the motor. So the kilowatt rating, we're going to look for the horsepower rating on the motor because that's its output. Or if it had a kilowatt rating, we could read it from here, but that's left blank in this one. So now we have to multiply the horsepower to get our power rating. So power equals 746 watts times by our horsepower, 5.36 HP, to get our actual power. So pull out our calculator. 746 times by 5.36, and we get 3998.56. They were after a kilowatt rating, not a watt rating, so we actually only put this down as 4 kilowatts in this question. Now moving on to question C, calculate the full load input on kilowatts on the motor. So this is a 3-phase motor because we're told it's 415 in delta. So our power formula in this case is power equals square root of 3 times I line times V line times cos theta times efficiency. So in this case, we don't have an efficiency, so we're going to use 1. Root 3 is a constant. I line is our 8.52 times by our 415 times by our cos theta. And that will give our power. So we have square root of 3 times 8.52 times 415 times 0.82, and we get 5021.83 watts. They wanted the full load input in kilowatts, so it's actually 5 kilowatts. What are other questions? So next one, the nameplate states the motor has a protection rating of IP53. What does the term IP mean? So that either means ingress or international for the I, and P just means protection. So either of those would be acceptable answers. I keep my answer sheet, confirm that for you. Where if I put it? So yeah, so international protection or ingress protection. Now, what type of protection is indicated by the first digit? So the first digit is physical protection, so dust, fingers, tools, things like that. So protection against solid objects, dust, anything you want to put there. What is indicated by the second digit? That's protection against ingress of water, so can water get in? So pretty easy questions. What would be the typical connection for a 3-phase 400 volt 20 kilowatt motor? So you would never connect a motor like this in star. The reason for that is once you're getting 20 kilowatts, it's quite a big motor. You want to be very efficient with your tools and materials. Star is a very inefficient way to connect up a 3-phase motor because you end up with a third of the power. So you've got a bigger motor for no reason. So that's why star is not an option in the answer sheet. You'll see you've got delta connection, you've got direct online starter, and you've got star, delta, starter. So they're the three ways that they want you to say that you typically connect up this motor. And then the next question, the motor is to be started direct online and protected by a thermal overload unit and HRC fuses. The thermal overload unit is incorporated in the DOL starter and protects the motor from overloads. Briefly explain the term overload as it relates to the thermal overload. So um, the overload is a bimetal strip that exhausts or is heated up based on the current going in. So larger current that a current larger that the current setting of that's horrible English. That is sustained over a lot. Operate the overload. I don't like how they've worded those myself. Uh, you set the overload to a specific amount of current, and once there's more current than it's set to, it will be too warm and it will open circuit its contacts. Is the way I would normally put it. Yeah, but their answer is apparently correct. One thing I should point out with the kilowatt horsepower one is they did say accept answers using 750 watts in the calculation. And even if it's in the calculation because you're rounding to 4 kilowatts, that extra 4 watts is irrelevant.